a lot, and thank you for the opportunity to speak. So Eric Adelberger told me that you actually say pendulums. Anyhow, I'm sure he knows best.
Unless you studied Latin and then it's pendulums.
That's right. But on papers, you're supposed to write pendulums, and we've been corrected for that. At least according to some people. So I also apologize to about half the people here who I've been discussing with a lot at JPL. This will be a lot of repetition for them. So I won't speak today about LISA science, but I will say that at low frequencies, so about below 3 millihertz, the LISA sensitivity should be limited by the acceleration noise on the free-falling test masses, which serve as the interferometer and mirrors. And the LISA sensitivity below that frequency depends on reaching an acceleration noise for the LISA test masses of something like a few femtometers per second squared per root hertz. I think it's not so different from what you need for advanced LIGO at around 10 hertz, but it's at lower frequencies down to 10 to the minus 4 hertz. And so this sensitivity at the low frequencies is very important for LISA science. At these low frequencies, I think the typical million solar mass black holes have their last stable orbit in the neighborhood of a millihertz. And so massive black holes are all at the lower frequency end of our band. And the extent to which we can lower the acceleration noise at low frequencies will determine, just to what distance we can see them, but also how long we can see them before their merger, which has a big influence on the LISA science because it determines how well you can locate them in the sky. And what I'm going to talk about today is LISA Pathfinder, which is a dedicated mission to understanding the limits to which you can put a test mass in a perfect free-falling orbit. So you can think of LISA and a lot of other gravitational measurements as basically differential accelerometer measurements, where we go to measure an effective acceleration, differential acceleration between free-falling test masses. We measure, which is coming from the gravitational wave, and we go to measure this against a background of noise from an effective distance measurement or displacement measurement with the interferometer, and against a background noise of non-gravitational accelerations on the test masses. And this way of looking at it kind of allows you to compare LISA or other experiments to a variety of other measurements, maybe even outside of gravitational waves. If you look at what we need for LISA, it's a few femtometers per second squared per root hertz. The best that's been demonstrated, I think, is what CaJAGWR is doing now, and it's several orders of magnitude higher and at slightly lower frequencies. So CaJAGWR and GRACE are geodesy missions around the Earth, and which are also clearly differential acceleration measurements, and we need to improve on this by several orders of magnitude for LISA. Also, the improvements that we have to make, I won't go into this in detail, but implicate a radical change in the design of the, if you will, accelerometry hardware, or anyways, the environment that the test masses are free-falling in. For instance, for GRACE and CaJAGWR, the test masses are basically connected mechanically to the spacecraft through a fine conducting wire. I can't even remember the material, but a wire of several microns thickness, which discharges the test mass, which removes a problem from cosmic ray charging, which we then have to deal with on LISA. But if you look at the thermal noise from that wire, it's orders of magnitude beyond what we can tolerate for LISA. So it's not proposable as a design. So not only does LISA represent a big leap in sensitivity, it represents a change in the kind of hardware we have to use to build the experiment. Couple this with the fact that on the ground, small force experiments, torsion pendulums or atom interferometers, but mostly torsion pendulums, do not reach these sensitivities, do not quite reach the femtometer per second squared level of acceleration. So these are the reasons why there's a dedicated geodesic motion flight experiment, which is LISA Pathfinder, and that's what I'll talk about today. And so I'll try to explain what we actually measure with LISA Pathfinder, what's the main measurement, what we'll learn with LISA Pathfinder and how this can be applied to LISA. And the other thing I'll talk about is, what can we say today about whether LISA Pathfinder will work or not, or reach its sensitivity goal. And so these last two items really speak to the sort of the overall noise budget for the mission, for the experiment, and that's what I'll try to get into today. So the general scheme for LISA free-falling test masses is test mass inside a satellite without any mechanical connections to the satellite. The satellite serves obviously to mount the entire apparatus, the interferometer, but it also serves as a shield from the dominant force disturbance, which is radiation pressure fluctuations from the sun. Now, the satellite feels radiation pressure, and so it is not a perfect free-falling reference. The test mass, in principle, it's shielded from the external disturbances, or principally shielded from radiation pressure. To maintain the spacecraft centered upon the test mass, you need some relative position measurement and some feedback to a set of precision thrusters. So once you've removed the sort of dominant external disturbance, what dominates the residual acceleration or acceleration noise on the test masses are disturbances largely arising in the interaction with the spacecraft itself. So that's what I'll get into a little bit today. In LISA, you have satellites which are distant 5 million kilometers. The basic idea of LISA Pathfinder is to look at two tests, take a LISA interferometer arm, compress it from 5 million kilometers down to about 30 centimeters, and measure the differential acceleration between the two free-falling test masses. Actually, maybe I'll back up just to say one quick point, just because I realized there's some confusion. So on LISA, you're measuring an effective gravitational wave acceleration in the background of non-gravitational accelerations on the test masses. In LISA Pathfinder, we have the exact same, or roughly the same force sensitivity. However, and in principle, we would be sensitive to gravitational waves also. It's just that we lose 10 orders of magnitude in sensitivity because you've shrunk the arm. So in principle, we are sensitive. And so when I say we're doing a factor of, when LISA Pathfinder aims at doing within a factor of 10 of the LISA sensitivity, it means LISA sensitivity to acceleration noise. It does not mean a factor of 10 in sensitivity to gravitational waves. I realized that there was some confusion with this. So in LISA, you have two test masses inside each satellite. Each test mass serves as the interferometer end mirror for a separate interferometer arm. And with two test masses, you can basically servo the satellite to follow one along its sensitive arm and the other along its sensitive interferometry arm. So basically, you do this drag-free control without applying any forces on the test masses along the sensitive degrees of freedom. For LISA Pathfinder, it's a much cheaper, simpler measurement where you have a single spacecraft and two test masses free falling inside the same satellite, and there's only a single measurement axis. So the satellite can either follow one test mass along that axis or the other. It can't follow both of them. And if it follows one, the other will just drift away by any DC difference in the local acceleration, or the local gravitational field is likely to be the dominant source. And this turns out, I'll get to this in a second, but this is an intrinsic sensitivity limit to the mission. So the LISA Pathfinder measurement is to servo the satellite to follow one test mass, use electrostatic forces on the second test mass in order to maintain a constant displacement between the two test masses, and then you look for any residual acceleration in the orbits of these two test masses, and that's read out with the optical interferometer. And so with LISA Pathfinder, we aim to do 30 femtometers per second squared per root hertz, which is about a factor 10 from the LISA goal. It's actually a factor of 10 divided by root 2 because it's differential acceleration. Additionally, we'll test, and so we should be able to get within about a factor 10 of the LISA goal at a millihertz. Additionally, we test the LISA local interferometer measurement, which is the measurement of the test mass displacement with respect to the satellite, which in LISA adds in with the interferometry measurement of the distance essentially between satellites. And we test this at the 10 picometer per root hertz level. And this is roughly, both of these first two objectives are using hardware which is representative of what you can use on LISA. What's not tested for LISA is obviously the big interferometry measurement, which is doing 10 picometer interferometry on a 5 million kilometer baseline. And all the complications which come with that, particularly the relative motion of the satellites. And, well, there are people who work on this here. So the idea is to test hardware that can be used for LISA and sort of start the commissioning phase of LISA, and also to create a physical model for the disturbances to achieving perfect free fall. I said that when you shield the test mass from the solar radiation pressure, what dominates the disturbances acting on the test mass or interactions with the satellite itself, what dominates that really turns out to be interaction between the test mass, which for us is a 2 kilo cube of gold platinum, and the immediate surrounding environment, which in this case is a conducting box, which also serves as a sensor, not for the sensitive interferometry axis, but it serves as a sensor for all other degrees of freedom, so the rotations of the test mass and the displacements in other axes. And the whole design of this sensor, which is a capacitive sensor, is to be able to provide sort of nanometer level sensing, but without introducing forces of order femtonewtons. Okay? The actual readout for the gravitational wave signal and for the main differential accelerometer signal for LISA Pathfinder is interferometer, and that's at the 10 picometer level. The design of this was not aimed at making the most sensitive sensor. It's designed to avoid force noise. That's the reason the gaps between the cubic test mass and the surrounding sensor are several millimeters, and this is largely driven by electrostatic concerns, electrostatic forces which fall off as the gap, or the gap squared, or even the gap cubed. It's also made out of metal, so in very high precision accelerometers, typically they use some optical glass, which is very stable, but we don't need sort of picometer sensing. It turns out that what is important for us, however, is shorting out any thermal gradients, and so using a conducting housing was chosen for this reason. And so again, when I talk about some of the leading force noise sources that I'll get into, I'm talking about things coming from the interaction between the cubic test mass and the surrounding sensor. I'll also talk about some of our experimental data for some of the leading noise sources. And so the data that we've kind of compiled in our noise budget is largely informed by measurements of small forces performed with torsion pendulum, in which some representative version of a LISA-like test mass is suspended as a member of a torsion pendulum. So we actually have two versions of this, one where the test mass is basically suspended on axis. And so in this case, we measure torques with respect to the test mass center of mass, which isn't really what we want for LISA and LISA Pathfinder. The gravitational wave signal is spoiled by translational acceleration. But for most of the noise sources that are threatening, there's a fairly simple model for linking force noise and torque noise. In other words, the sources of force noise that are interesting in flight produce also torque noise in large part. It's not true for all of them. So we've built another pendulum where the test mass is suspended off axis, again inside the relevant gravitational reference sensor, this capacitive sensor. But in this case, we're sensitive to direct forces acting on the test mass. And so we don't need to rely on any model for converting torque to force. So I'll describe really briefly the LISA Pathfinder measurement, and then I'll try to discuss our noise budget in terms of what I will call instrument noise and what I'll call sort of our science signals, and I'll get to that in just a second. So I described already the measurement we perform is we're measuring the differential acceleration between two free-falling test masses. If you look at the acceleration noise for LISA, which is really what we're interested in verifying, the acceleration noise of the test masses can be decomposed into a term which is fluctuating forces which have fluctuations in our measurement band. And there's a second term which corresponds to basically any steady force gradient, so df dx, or here we've divided by mass, and so this becomes a frequency, sort of a spring frequency squared, which multiplies then, even if that's steady, that will multiply any jitter in the spacecraft position to give us a force. It's basically like moving the suspension point of a spring. So, and for reasons which I'll get into, this term will likely be fairly small for LISA. And so the thing we're most interested in measuring for LISA Pathfinder are the stray forces that act on the test masses. So if you look at the interferometer signal on LISA Pathfinder, there's a term, this first term, which is what basically most interested in measuring, which is the differential force noise acting on the two test masses. Now, we measure this in a background of different, what I'll call sort of instrument noise. The obvious instrument noise comes from noise in the interferometer readout, so just our ability to measure the displacement. There's also a second term coming from right to left, I guess, which has to do with the baseline stability of the optical bench, which separates the two test masses. Turns out that if that expands and contracts, it winds up sort of moving the sensor around the free-falling test mass, and that converts through this omega 2p, which is a spring constant, into giving me a noisy force. Then finally, there's a satellite coupling term, which has to do with the imperfect satellite control. So this first term has to do with the jitter in the satellite's position compared to the free-falling test masses. If you think about it, if you move the satellite compared to these, with respect to these two test masses, sort of the differential force that you get has to do with the difference in the spring constants with which the two of them are bound to the satellite. So if the spring constants are exactly equal and I move the satellite, they basically get pulled with the same force and I don't see it. So I consider these three terms on the right instrument noise. And our source, or our science signal, are basically the stray forces acting on the test masses. So if I divide the problem in this way, I can say, what's the resolution with which we can measure the stray forces acting on the test masses? And then I'll get into, well, how big are those stray forces? So that's how I'll dedicate the rest of this talk. Actually, if there are questions, there's just a few of us, so you can ask. So what determines our instrument sensitivity? And actually, what I'll do here, I'll tell you in advance that this term is very small, as is this term. Excuse me. This term is very small, the baseline stability. This is just thermal expansion of the zero-Dürr optical bench. And the satellite coupling term are very small. So what are the instrument noise sources that are dominant? The first is the readout, which is optical interferometer, and that needs to achieve 9 picometers per root hertz. And here this is just a conversion of 9 picometers per root hertz converted into acceleration. And this is relaxed below 3 millihertz. The other noise source is the pink term, which is actuation. So I mentioned that For LISA Pathfinder, on the second test mass, we have to apply actuation forces. Otherwise, the two test masses will just drift apart and one will hit the satellite. Okay? So we have to apply a force on the second test mass. Turns out it's difficult at these frequencies, at a millihertz frequency, to apply a perfectly stable force. Okay? And so what this second curve here, this pink curve, corresponds to is having to balance a force which is 1/10 of a nanometer per second squared, or excuse me, an acceleration difference, which is 1/10 of a nanometer per second squared. And if you do that with something like 10 ppm per root hertz stability, so 10 to the minus 5 per root hertz stability, you get this curve, which turns out to be something like 10 femtometers per second squared. And this is what limits the LISA Pathfinder measurement at all low frequencies. And I call this an instrument noise because you don't need this on LISA. There is no actuation along the sensitive axis on LISA. So from the standpoint of force noise sources for LISA, this is an instrument noise. You could compare these with the goals for the mission, LISA Pathfinder mission, and the goals for LISA itself. You could see that the instrument sensitivity is a factor of a few below the mission goal at a millihertz. I'll try to say now how realistic it is that we can meet this. The other thing is this enables us to get within a factor of 2 or so of the LISA goal at a millihertz. And if you go ahead and put some of the calibration sources for LISA, so the binary white dwarf systems in our galaxy, you can see that there's more than, if we can detect force noise at this level and demonstrate that there is no excess force noise at this level, this is more than sufficient, at least from this noise source, it's more than sufficient to begin doing astrophysics with LISA, which was some of the rationale for the mission. So I'll talk really briefly about the instrument limit. For the interferometer, this is 9 picometers per root hertz. This has already been demonstrated on the ground. This has been demonstrated, these are with fixed mirrors. Okay, so this has not been done with live test masses yet, and there is something to be said for that. There's all kinds of crosstalk which enter. But from what we've demonstrated on the ground, the interferometer is ready. This is a Mach-Zehnder heterodyne interferometer. Again, for LISA, one of the important aspects is the local interferometry measurement of the test mass compared to the satellite. And again, that's with a test mass which is wiggling in all degrees of freedom, not a fixed mirror. And this is also an important demonstration for LISA. I said that the satellite coupling term is small. So why do I say that? Basically for 3 reasons. First of all, when we first got into this business, there was a lot of fear of getting uncontrolled force gradients, particularly from patch effects, from stray electrostatic fields inside the sensor. And those are effects which go as the gap cubed, or 1 over the gap cubed, I should say. That's why we have several millimeter gaps. It turns out we can measure the stiffness. You can imagine the force gradient, or stiffness. You can do an experiment where you just basically move the sensor, which is the dominant source of force stiffness, with respect to the test mass. You just wiggle it, and you see the coherent force which is excited, which is just proportional to its displacement. Now, there are force gradients that we know about which come from sensing voltages, which we apply. There's for measuring with the capacitive sensor. And so this is a plot of the measured force gradient as a function of applied voltage. And you can see, and this is well modeled, you can see when I turn off the voltage, what's left is a very small fraction of the stiffness which is modeled, with the stiffness which we know has to be there. So the uncontrolled sources of stiffness are just very small. It turns out there's more fundamental reasons why this noise source isn't so worrisome. If you look at this noise source for LISA and for LISA Pathfinder, you should have several nanometers per root hertz jitter in the position of the satellite, which is determined by the force noise in the thrusters which act on the satellite. And this is, if you multiply a few nanometers times something like 10 to the minus 6 per second squared, which are the typical spring constants, this becomes femtometers per second squared type acceleration. So this is a big noise source. However, there are two things to keep in mind, is that while the spacecraft is jittering with nanometers of displacement, we measure that displacement with 10 picometer accuracy. Additionally, you can do this in flight. You can do this same experiment to measure the force gradient. You can basically move the satellite back and forth and see the motion of the test mass. And so in this way, you can measure, you can measure the force gradient, you can measure the displacement, so you can calculate the force. So you can remove this term in software or in analysis afterwards. The other thing on LISA Pathfinder is that the coupling term is basically a difference of spring constants which matters. And again, we can measure that difference of spring constants in orbit just by dithering the spacecraft position. And so we can measure it, and then by applying electrostatic fields, we can tune it to be 0. Okay, so you can basically make this noise source disappear. I won't say much at all about this, but the other thing which enters in spacecraft coupling is, are the thrusters which pilot the spacecraft actually precision enough to not introduce excess noise? And it looks like that's possible. They need to have something like 10 to the minus 7 newtons per root hertz, and that's been demonstrated at least on the US side. So I'll get back to the last instrument noise source, which is gravitational balancing and our imperfect compensation of this. So why do we need to apply a force, or how big is the force we need to apply? That's set by just how big the differential acceleration dc is on the two test masses. So if there's any imbalance in the local gravitational field, the two test masses will separate with a certain acceleration. We need to compensate that. So additionally, we can only compensate that with a certain level of stability. And with the electronics we have, it looks like it's something like 5 to 10 parts per million per root hertz. So to make this noise source small, we need to gravitationally balance the satellite to something like 1/10 of a nano-G. Okay? And all the models that we have say this is possible, but it means it puts very tough requirements on the precision with which you know the mass distribution on the satellite and the precision with which you assemble the satellite. It turns out that basically the two test masses are 2 kilos, 30 centimeters apart. Each of them is inside a vacuum can, which is about 15 kilos. If you calculate the gravitational attraction, it gives you something like 50 nanometers per second squared. So if you don't do anything, the two test masses will basically attract, or will fall in towards each other. So what you do is you basically put mass outside of the two test masses, which pulls them out. And you try to balance this. So if you do nothing, you might get 100 times worse this level. So we need to balance it to something like to about a part in 100. And so this is a tungsten balancing mass, which is basically placed just outside the two test masses. And it turns out that has to be placed with something like 70, 100 micron precision. So it's not trivial assembly of the satellite. But all our indicators say that this will be reached. We've also tested the electronics. The electronics at a millihertz seems like it's noisy at something like the 8 to 10 parts per million level. And so this is likely our dominant limit of the instrument sensitivity, but it should not interfere with the mission goal of getting, let's say, 10 femtometers per second squared per root hertz. It turns out if we screw up the gravitational balancing, if the gravitational balancing turns out to be much worse than what we had analyzed it to be on the ground, or if the actuation is noisier, is there any way out? It turns out there is. You can basically imagine, if you don't apply any actuation, the two test masses will drift apart with something like 1/10 of a nano-G acceleration. You get parabolic flight with 1/10 of a nano-G. So you can only do this for something like a couple hundred seconds, and then you start sending the sensors into the nonlinear regime. You start getting displacements of tens of microns. However, in those few hundred seconds, it's been free falling without any actuation. What you can do then is kick it, so apply a very large force, an impulse, which then sends it on another parabolic flight. And so, if you look at the time series of what the displacement is, you get this series of parabolic flights. If I convert that then to acceleration, I'll have an acceleration which is basically constant, plus the low frequency acceleration in the absence of actuation, except during the moments in which I applied the impulse. So you need a clever way of analyzing the experiment, but in this way, you can have the low frequency acceleration of the test mass without the actuation. So this is a possible solution to this actuation issue. So that's the sort of instrument sensitivity. How big are the actual noise sources that we go to measure? In other words, the acceleration noise sources on the test masses. What can we say about them? That's how I'll spend the rest of this talk. Again, actually, I would have been wise to grab a pointer. But our instrument limit is something like 10 femtometers per second squared per root hertz at a millihertz, which again is within about a factor 2 of what we need for LISA. I'll go through several of the noise sources, but first I'll just list them. And I apologize, this plot is not nearly as, let's say the error bars on this plot are considerably larger than what you would have for LIGO. This is not as you'll see, there's more uncertainty in some of the parameters than what you have for LIGO. But the noise sources we'll talk about are gas damping, electrostatic effects, basically the average electrostatic field acting on the test mass charge, laser radiation pressure fluctuations. So it turns out the milliwatts of laser light that you have fluctuate at something, the power will fluctuate at something like 100 parts per million, they said, at a millihertz. Grazie. Self-gravity fluctuations. Any motion in the mass on the satellite will give a changing gravitational field. There are magnetic effects of the local magnetic field interacting with the test mass magnetic moment. And I'll describe a few of these anyways, what we know about them. So this has gotten a little bit of attention lately because basically we're not accurate in our original modeling of this problem for LISA. It's residual gas damping, which you can just express the force noise in terms of the fluctuation dissipation theorem and the viscous gas damping coefficient. So it's easy to do a sort of an order of magnitude calculation of the number of impacts times the typical thermal momentum. If you put the test mass in motion, you can calculate the difference in the number of impacts on the front side and the back side of the test mass. You can calculate a coefficient of damping. Turns out you should consider also the shear impacts on the other faces of the test mass. You should also consider the correlation between the incoming process and the outgoing process of re-emitted molecules. But it turns out this is also very incomplete, and this is relevant also for LIGO. We've understood in the meantime, at least the advanced LIGO, that a molecule which hits the test mass doesn't just disappear in our constrained experiment volume, does not just disappear into the bulk. It hits the surrounding sensor, absorbs, is re-emitted, and hits the test mass again on the same side. And so you get repeated impacts on the same side of the test mass. And so the impulses from repeated impacts are correlated. Okay? And it takes a long time for a molecule to sort of random walk off this side of the test mass and start going and hitting you on the other side. And so there's sort of a correlation time to the impacts. It turns out this increases the force noise considerably. It's about a factor of 15 in power. I won't get into this, but we discovered this. We observed this first in the laboratory before realizing this effect. Basically, our torsion pendulum dissipation factor, or quality factor, depended much more strongly on the pressure than we thought it should, than what we had calculated. And what we found in the lab works pretty well at the 10 to 15% level. And so this noise source is probably our biggest noise source about which we're fairly secure. This depends on the square root of the pressure. And the pressure that we should reach on LISA Pathfinder is about 10 to the minus 5 Pascal or 10 to the minus 7 millibar. This is limited by the fact that we're using these passive activated charcoal getter pumps, which have a very, very slow pumping velocity. And actually this problem, so this is at something like the 6 femtometer per second squared level. This is too large for LISA. So basically on LISA, we're going to have to reach a lower pressure. On LISA, the idea now is to vent to space. So basically to take a big tube, which reaches the vacuum chamber holding the test masses, and bring that out to space. This isn't as obvious as it sounds because it turns out the spacecraft is a lot messier and dirtier and desorbs a lot more than is reasonable to just allow the test mass to be sitting there in the middle of the satellite. Basically, the satellite is a filthy environment. And so to take advantage of the wonderful vacuum of space, you need a big tube. The other thing, this is really white noise and thermal equilibrium noise, so it's uncorrelated with any other noise source. In flight, we don't have a pressure gauge, so we don't actually have a way of measuring the pressure. And so if the pressure were much worse, in principle we wouldn't know, or excuse me, if the force noise that we measure is much worse, we wouldn't know if we could attribute this to excess pressure or not. And it turns out there's a way of getting at this, which I'll describe in just a sec. Another noise source which is worrisome or potentially worrisome are thermal gradient forces. So if you have one side of the test mass sees a hot environment, the thermal photons emitted from that environment will impart more momentum on the test mass than those from the cold side. This is a radiation pressure imbalance which comes from any difference in temperature. Turns out there's also a radiometric effect where the hot molecules on the hot side will impart more pressure to the test mass than those from the cold side. There's also an outgassing effect where if you heat up one side of the test mass, there'll be more desorption from that side, and that will also give you a force, and that's not so easy to calculate. So for this noise source, we've actually made measurements in laboratory, and it turns out that this is about 100 piconewtons per Kelvin. About half of this is outgassing, and that's not enough to become a real problem for us. So if you have 100 piconewtons per Kelvin, this is what we measure in the lab. It turns out you need something like 10 to the minus 5 Kelvin per root hertz stability in the temperature gradient. And that's roughly what we calculate now for the thermal modeling of the satellite. Looks like even in a worst case scenario, at least at 10 to the minus 3 hertz, this shouldn't be a problem. In flight, we can also change the temperature. We have heaters and thermometers, so we can apply a temperature difference and basically do an in-flight calibration of this. It turns out this is useful also for that gas damping problem. Because the radiometric effect is proportional to the pressure, if the pressure turns out to be much worse, this overall coefficient, the d force d delta t, will be much larger. And so in this way, if for some reason the pressure is larger and our gas damping is worse, we can't directly measure the pressure, but we can detect it by performing this thermal gradient experiment. So there's also magnetic effects. You know, there's energy of magnetic moment, a scalar product with the magnetic field. So any gradient of the magnetic field will suck a test mass with a non-zero magnetic moment. So we need that the magnetic moment of the test mass is small. There's also an induced magnetic moment, which is proportional to the susceptibility. And so right away you could see that if you have a steady gradient and fluctuations in the magnetic field, The fluctuations in the magnetic field create a magnetic moment which is noisy, which then interacts with the gradient to give you a noisy force. There's also any fluctuations in the gradient interact with both the induced and residual magnetic moment. So the test mass is gold platinum that's designed to have a nominally zero magnetic susceptibility. Turns out that it's something like 2 × 10⁻⁵, which is good enough. The magnetic moment is small enough. We happened upon another noise source that we hadn't thought of at the beginning, which is, if you have a time-varying magnetic moment and a time-varying field gradient, you can get down conversion, such that even if these are fluctuating out of band, they can mix down to millihertz frequencies. It turns out there's a natural mechanism for this. There's also, in addition to the sort of static susceptibility, there's a Faraday susceptibility. Basically, the induced eddy currents in the test mass produce a magnetic moment. In this way, magnetic field, in principle, at any frequency, will cause the moment to fluctuate at that frequency, and that will mix with the magnetic field at another frequency to down convert to give you force noise at low frequency. Turns out there's a natural cutoff to this. Well, the test mass is surrounded by a vacuum chamber and a conducting sensor. There's a skin effect, and so at high frequencies you don't get magnetic field penetration. Basically starts to behave like a superconductor. So this turns out to be around 1 kilohertz. So for this effect, again, it looks like the static magnetic moment properties are under control. What we need, though, for this down conversion effect, which we didn't realize at the beginning or wasn't part of the noise budget for LISA or LISA Pathfinder, turns out that this down conversion basically requires that the field fluctuations at all frequencies up to a kilohertz have to be below something like a nanotesla per root hertz. And this looks compliant with sort of typical magnetic cleanliness requirements that industry can deal with, which are basically sort of RMS field measurements. But this is something that for which today we don't have a good measurement. We will be doing tests on the satellite to make sure that this is reached. But this was a kind of a surprise. And so this is probably conservative, but this is the noise budget here, this pink curve for magnetic down conversion. And this is basically, at least if you believe the sort of industrial noise budget that we've put out, this is likely our biggest noise source. We think that there's a lot of margin here, but the last individual noise source I'll talk about, maybe briefly because I could see, are stray electrostatics. So you've got a test mass inside a conducting shield, which should be an equipotential. Well, first of all, the test mass charges up. There's cosmic ray charging, which is sort of a Poissonian or even non-Poissonian stochastic process. And additionally, the equipotential of the sensor which surrounds the test mass isn't a perfect equipotential. They're stray fields. If you measure sort of the difference in average electrostatic potential between domains of roughly a centimeter on different parts of the same conductor, you can get differences in voltage or differences in potential of order tens of millivolts. This has been seen also in Kelvin probe measurements. We can measure this with a torsion pendulum. But the interaction between the test mass charge and the surrounding electrostatic field will give you force noise. It gives you force noise if the surrounding electrostatic field is static, or the static part of the surrounding electrostatic field will interact with any noise in the test mass charge. And since the test mass charge, it's sort of current shot noise, white current noise, becomes 1 over F in charge noise. It's basically a random walking charge on the test mass. And this gives you 1 over F noise in force. By the same logic, if you have sort of a steady part to the test mass charge, if that's not time average 0, or when it's not 0, and it won't be 0 because it charges up over the course of a day, that non-zero charge will interact with any noise in the surrounding electrostatic field to give you force noise. I mean, this is pretty simple physics. We've verified this. I won't go into the details of this experiment, but we can make the test mass charge fluctuate randomly, basically by applying large and compensating photoelectric currents, which are designed to not change the DC value of the test mass charge, but give you a large shot noise. And if you do this in the presence of an applied stray field, you can predict very well the corresponding force on the test mass. We've done this with a torsion pendulum. Since the test mass charge interacts with some average field, it turns out that you can get around this noise source, at least to a large degree. You can measure the average stray field basically by, if you modulate the charge on the test mass, this results in a modulated force on the test mass, which is proportional to the average stray field. And that's the average stray field that you need to then compensate to remove the coupling to the test mass charge. And so we can do this in flight. We've done this in the lab. It turns out you can measure this at the sub-millivolt level, and that's more than plenty to null the effect to within our measurement resolution. We've also made measurements of, in addition to measuring this sort of average field, you can also measure how much it fluctuates. And here we've done this down to very low frequencies. We're limited by our force resolution above 10 to the minus 4 hertz, and we don't detect any excess force noise. That level that we measure is a couple hundred microvolts, or the upper limit we can put is something like a couple hundred microvolts per root hertz. And it turns out that's about a factor 2 or 3 more than what you want for LISA. So here we can say for certain this won't be a noise source for LISA Pathfinder. It might be for LISA, but what we know now is it's consistent with 0, and the upper limit we can put is about consistent with the overall LISA goal. One of our current on-ground laboratory efforts is to improve this sensitivity. Additionally, this is something we can measure in flight. So these two noise sources, the fluctuations in the average field and the random charging, are both well below the instrument limit, and they're below the levels that we need for LISA. So at least for the noise sources which are in our noise budget, it looks like we're compatible with the goal for LISA Pathfinder. You could say, well, I don't really care about your noise model. You don't know all the sources in the noise model, or excuse me, you don't know all the noise sources which can act on the test masses. So what can you tell me, if you do just sort of a global force noise test, how much force noise do you measure? Is it compatible with the LISA goal? And this is a measurement that we do in the lab. Basically, we use the torsion pendulum. The test mass is suspended inside the gravitational reference sensor, subject to all the forces that can arise in the interaction between these two. And we just look at it for a couple days. What's the force noise? We've done this with 2 pendulums. The blue curve is with a tungsten fiber. Tungsten is what we and other groups have used for torsion fibers forever. It has a Q of a few thousand, which means ring down time of a few days. And you can see the force noise that we've measured are these data points, and this blue straight line is the thermal noise, just from the fluctuation dissipation theorem of just kT of energy in the harmonic oscillator of the torsion pendulum. Now, what we can attribute to excess force noise, which could come from our sensor, could come from anything else. There's all kinds of other noise sources, environmental noise sources acting on the torsion pendulum, which have nothing to do to our sensor. But if you say, attribute everything to the sensor, how much is the force noise? And it's basically, it's this difference between what we measure and the thermal noise, which is background. Well, basically we were about 10% above the normal, the force noise, and so this was kind of unsatisfactory because maybe you're not calculating correctly the background noise. Now we're using a fused silica fiber, which turns out works just fine as a torsion fiber. The intrinsic Q is around 1 million, so the ring down time is around 5 years. And it made the thermal noise floor just sort of almost fall off the graph. If you repeat the experiment and you measure the force noise, and again you take the difference, here it's clear we have a force noise excess. Okay, there's no way we're miscalculating. We don't know yet if this is coming from the sensor or coming from the environment. We suspect it's the environment. However, if we're not able to rationally explain this difference, you would have to look at doing something where you make a measurement in the absence of the sensor. This is something we're actually looking at. But how large is this difference? It turns out this difference here is smaller than this difference here in absolute force noise terms. The logarithmic scale kind of fools you. So how big is the force noise? If I look at that green curve, that turns out to, if I convert that to a LISA test mass, convert it from torque to force and into acceleration noise, gives me a sensitivity which is something like 50 femtometers per second squared per root hertz at a millihertz. So at a millihertz, it's something like 60% above the LISA Pathfinder goal. Now, don't get me wrong, this isn't saying that we've already demonstrated the LISA Pathfinder goal. In these measurements, we use a hollow test mass, so this is only sensitive really to surface forces. We use a hollow test mass because suspending a heavy test mass, a full 2 kilo test mass, would require us to use a very thick fiber, which would be much less sensitive. So if the most dangerous noise source are these surface forces, we optimize for that by using a very light test mass. So LISA Pathfinder will be sensitive to things coupling to the bulk test mass, like magnetic noise, like self-gravity noise, whereas we're not sensitive to that in the laboratory. It's also sensitive to all the coupling to the spacecraft motion and the spacecraft control forces. And so we're not doing that in the laboratory. And also, finally, it'll be sensitive to the full space environment, so the thermal fluctuations you'll have on board, the charge fluctuations. I'll just close with a couple pictures. So this is actually the flight model spare. Basically 3 gravitational reference sensors have been built. 2 of them will be launched in orbit, and the 3rd is in our laboratory in Trento. And we're doing some final checkouts, testing for force noise sources, but also just kind of calibrating, using electrostatic force calibrations. I didn't even talk the electrostatic discharge we need to do with the test mass, so sort of calibrating this electrostatic discharge. The experiment will launch in mid-2012, I think is the most probable launch date now. This is actually, they're building the spacecraft in Aztec now, or doing some testing. This is an enormous shaker. And this here is one of the European clusters of micronewton thrusters. There's a blank hole here which will house the American package of micronewton thrusters. The last comment I'll make is, one thing we're working on in the laboratory is to have a pendulum which is as sensitive as LISA Pathfinder, so that if we see something strange with LISA Pathfinder, we can measure the effects, at least certain effects, surface noise effects, with the same precision on the ground. And sort of to do extended experimental investigations that we can't do with LISA Pathfinder. LISA Pathfinder will have about 3 to 6 months of measurement time, depending how you count it. But, and so currently in the laboratory with the fused silica fiber, we're well above the noise floor of the thermal noise floor. We're trying to understand this. You don't see us here, but we're actually limited by sensor readout at all frequencies except the pendulum resonance, which is around 2 millihertz. And so we're working on improving our readout from something like tens of nanoradians per root hertz to something like a nanoradian per root hertz. So at millihertz frequencies. So we're working on an interferometric wavefront sensor to do this. Okay, I'll close. So this is a picture of the European LISA Pathfinder collaboration. There's about 200 people who participated in the last conference we had in Trento. And then these are my direct collaborators in Trento, and the bold-faced names are the names which contributed most to the experimental measurements that I showed you. So, oh well, thank you. If there's any questions. Bob.
Yeah, I wonder about the noise lines. They didn't seem to match in shape either. The noise levels.
Yeah.
So that's presumably viscous damping.
Yeah, that's right. So, that's right. We know with the tungsten that we're dominated by internal fiber dissipation, because if you change the fiber, the quality factor, or the dissipation goes way down. With the fused silica, we know that part of it is viscous, and actually the curvature there, would become flat at high frequency, because there is some noise, there is a contribution from the gas. To be honest, we don't really have a proof that this is structural damping. In other words, it's possible that there's some magnetic viscous damping. And so the point, if you want to be precise, I know what the Q is here, which is the resonant frequency where we measure basically through the ring down of the pendulum. At that frequency, we know what the damping is. It's possible that this is not correct. It's possible that this should be flat.
But it's not possible it's up an order of magnitude or something.
No.
And you say you know the sensing noises.
Well, yeah, I should have prepared. So we actually do these measurements with two sensors of roughly similar accuracy. One is actually the capacitive sensor, which is the rotational readout for LISA or LISA Pathfinder. And the other is basically an optical lever, optical autocollimator. And so we extract the torque noise sort of through the cross-correlation of these two signals. And if you look at the noise spectrum for the two instruments separately, you see that they coincide for half a decade of frequency around the resonant curve. At higher frequencies, we're limited, the sort of the white readout noise is different. At lower frequencies, I'm not sure, but the two readouts definitely read a different, you don't get exactly the same readout, and so there's a readout issue even at the lower frequencies. Are there other questions?
You mentioned that you needed muscles to micrometer accuracy.
Well, something like 100 microns. It's not quite, yeah. That's in the positioning. In their machining, I can't remember the mass requirement, but I don't think it's actually too bad.
I was just wondering how this is going to withstand sponge.
That's right. Yeah. You. That's a good point. So there are also alignment issues of like the interferometer compared to the capacitive housing, which immediately surround the test masses. All of that has to be measured both before and after vibration testing. So the before and after launch, one is the effect of shaking it, and the other is the effect of going into 0G, which also produces a distortion. And so that's been analyzed fairly well. This second aspect of going into 0G was analyzed from the standpoint particularly of the your ability to balance the gravitational field. And anyhow, I've leafed through the analysis which says that it's not a big issue. Yeah. It's unlikely that the gravitational balancing is much worse than our goals. In that you need to balance, if the dominant sources of the gravitational field are the vacuum chambers which are holding the two test masses. And if you just sort of calculate, well, if I didn't do anything, how bad would the gravitational balance be? It would be something like 50, 100 times worse than what we need. Now with margin, that means you're trying to compensate it maybe to a part in 1,000. And the resolution of the calculation is much better than that. I mean, it's very simple. It's just summing mass divided by distance squared, essentially. However, it puts requirements on the instrument providers, like the electronics boxes, that they know their mass distribution better than they would normally have to know it for other missions, let's say. And then also the kind of satellite assembly, at least for things which are near the test masses, has to be quite precise. So, but I mean, 100 microns isn't so intimidating. It's that there's lots of pieces.
Somehow I had the micron, so.
Ah, okay. The machining tolerances are of order 5, 10 microns here and there, but I think the most critical placement is probably that this compensation mass, which basically you glue it as closely as possible to the test mass itself. The farther you are away, the less critical the position is, but the more mass you need. And so we're very mass critical. In fact, they've threatened time and time again that you have to remove mass. So putting 50 kilos a meter away wasn't an option. Putting a ½ kilo 2 centimeters away was. I was going to add something. I'm sorry, I forgot.
One question.
Of course.
What's happening with the bump in the middle on the Gilco? I'm just wondering. Where is the beginning?
Here? I guess I'm not sure what you're talking about.
There was three curves. There was a calculated, measured, and something else. And
What was the quantity?
Huh?
What was the physical quantity? It was
I think it was a displacement.
The bottom left, the
Bottom left, yes.
here.
no, before. That.
That one.
Ah, yes, that's right. This is
Plus
a measurement of thrust noise. So this was performed on so there's an American contribution to the mission, which is the DRS, which is being directed, at least in part, by JPL. And this is with the US colloidal thruster. And yeah, so they're measuring thrust noise both with and without the thrusters turned on, let's say. And so the green and the blue curves basically overlie each other, and that's the measurement background noise. So they detect no excess noise. And yeah, I'm sure that's a microseismic peak. Yeah. I can't remember the exact nature of the thrust stand in this measurement, but I remember there was a big issue of converting sort of common mode rejection, if you will. So, acceleration of the suspension point converting into a rotational. We also have this issue with the torsion pendulum, but it's almost negligible. And we're not particularly interested at 1 hertz or whatever, 0.15 hertz or 5 seconds. Yeah, it's more or less. Yes, LIGO people probably recognize that. Thank you.